video is the second in a two-part series addressing the safe operation and design of biogas capture, storage and combustion systems. This video has been developed for personnel such as engineers who are responsible for the safe design or installation of biogas capture, storage or combustion technology. It will address considerations during the siting of covered anaerobic lagoons or CALs and the establishment of exclusion zones. The safe design of CAL covers for protection against damage will be discussed, along with the considerations for the design of biogas trains. It will conclude with cleaning system for the biogas stream to protect infrastructure. CALs and associated equipment are usually located at a distance from processing operations and residents due to the explosive risk. Where practical, CALs should be located on the site well away from traffic, areas where people are working and neighbouring residents. A minimum distance of 50 metres is recommended, subject to site limitations. As much as practical, ignition sources should be minimised near the CAL and biogas train. These include vehicles, electrical equipment, hot work such as grinding and cutting operations, and open flames. There are zones around the CAL where ignitable concentrations of biogas may exist. Electrical equipment should either be located outside any hazardous area or be compatible with operations in that designated hazardous zone. Control panel enclosures should be rated to IP55 at a minimum. An exclusion zone of at least 3 metres is recommended around the CAL and associated inlet and outlet pits so as to prevent public and animal access. Animals, especially kangaroos and dingoes, have been known to severely damage CAL covers. The exclusion zone should be secured using a security fence. Security mesh is recommended and the fence should be at least 1.8 metres in height. Exclusion of children is critical, even though most CAL sites are usually remote from residences. All access points should be locked. Safety signs should be erected near the main entry point to inform of the hazards and required safety measures within fenced area. Recommended signage include no entry, authorised personnel only signs, exclusion of ignition sources signs, biogas properties and hazard signs, deep tank signs. The biogas pipeline must be clearly identified with signage to prevent damage by third parties. Tall objects such as light stands, power poles and trees should be positioned at a suitable distance to eliminate the possibility of their falling on the cover during storms or due to the failure of the supporting structure. Vegetation should be controlled in the surrounding areas to reduce fire risk to the cover in the case of bushfire or where a fire event occurs nearby. Where ember attack is a realistic possibility, consideration should be given to fire suppression systems to protect the CAL cover. The cover is an integral part of the CAL and it is imperative that it is not compromised. Holes in the cover will not only allow loss of biogas to the atmosphere, but also create a potentially hazardous environment. The cover design should include features that reduce the likelihood of damage. Meat processing CALs have a propensity to accumulate scum under the cover despite best practice pre-treatment. Biogas collection piping should be at least 500 millimetres above the maximum operating water level so that the risk of scum, foam or mousse entering the collection system is minimised. Overpressure release systems prevent the cover from overinflating and possibly tearing in the event the biogas cannot be withdrawn for any reason. Several options have been used in Australia. Safety spears are simple pressure release devices, however they are vulnerable to blockage by scum under the cover, which may reduce their effectiveness and impose additional stress on the cover. They are best placed well within the cover perimeter to avoid biogas release at angles near horizontal to the ground. Hydrostatic release valves use a depth of liquid, typically water, to prevent biogas release below a set pressure. The advantages of this device are its simplicity and that it is unlikely to be compromised by scums. It also releases gas remotely from the CAL. The disadvantage is the requirement for constant topping up of the liquid and the small margin of error, especially on hot summer days, which can lead to excessive biogas release. Weighted flaps can be used instead of spears to avoid penetration below the cover. They are best placed well within the cover perimeter to avoid biogas release at angles near horizontal to the ground. When joining the large HDPE sheets that make up the cover, seam welds should use split head wedge and/or extrusion welding techniques to join HDPE sheets. Penetrations through either the CAL liner or cover, for example inlets and outlets and safety spears, should be reinforced to minimise the risk of tearing. Stormwater removal systems should be designed to remove large volumes of accumulated stormwater on the cover surface, which can potentially strain the cover and interfere with biogas collection. It is recommended to avoid installing electrical items on covers such as stormwater pumps unless fitted with temperature cutouts. A hazardous area analysis consistent with Australian standard for explosive atmospheres classification of areas is recommended to assess the extent of suitable zones for separation of potential biogas release points from identified hazards. Where possible and appropriate, large exclusion distances for potential ignition sources should be provided to minimise the possibility of flash fires in the event of major releases from covers. Biogas pressures are typically low for meat processing industry cows. Biogas pressure upstream of the blower and under the cow cover is usually less than 0.1 kilopascals. In some cases, it may be under negative pressure for some systems. This is compared to standard atmospheric pressure at sea level, which is 101.3 kilopascals. Downstream of the blower, a typical biogas delivery pressure to the flare using centrifugal blowers is still low at less than 5 kilopascals. Higher pressures may be used for delivery to gas boilers and cogeneration plants. A manual isolation valve is recommended in the biogas pipeline adjacent to the cowl to permit isolation of the biogas train from the cowl. In laying out pipe runs and equipment, recognition should be given to the damage that could be caused to nearby objects by potential gas releases and ignition sources. Typical impact distances due to thermal radiation from a small jet fire are small, usually order of 3 metres or less. Consideration should be given during design to isolation strategies, particularly where long biogas pipe runs are planned. Fire escalation can occur when flames cause grass fires to propagate. Open areas should have potential fuel hazards minimised to reduce escalation. Stainless steel pipeline construction is recommended for above-ground biogas piping as it has good corrosion resistance and fire protection properties. Refer to Australian standards for steel pipe systems. PVC and HDPE may be considered for biogas piping, but generally it is required to be underground to protect against fire risk. Refer to Australian standards for gas distribution networks using plastic pipe systems. The impact of high biogas temperatures should be considered for plastic piping. Under Australian conditions, biogas temperatures may be higher than the permitted temperature tolerance. Any biogas recirculation system must take into account heat added through the recirculation blower. When working with plastic piping, there is a need to beware of static electricity discharges, especially when working on the pipeline. Ensure good earthing practice. Condensate can form in the pipes and may contain hydrogen sulphide, which is corrosive. It needs to be drained. Knockout pots must be installed at low points in the biogas pipeline to remove condensate and to ensure hazards such as mousse or scum do not enter the blower. These units must be manufactured from non-combustible material. The volume of condensate may increase substantially during periods of flare outage due to biogas cooling in above-ground stainless steel piping. The pipe should grade back to the cowl or a knockout pot at a constant minimum slope of 2% to prevent accumulation. How blower to the flare is designed depends on the requirements in the relevant Australian standards for different anticipated biogas fuel loads. Large meat processing plants and independent renderers who are treating a high proportion of their raw wastewater through cows, for example, will typically produce in the range of 5 to 20 gigajoules of energy every hour. Smaller abattoirs, on the other hand, will typically produce less than 5 gigajoules of energy every hour. The nature of the safety shutoff valves, for example, would vary significantly for these two different biogas fuel load. In terms of design and installation standards for biogas systems downstream of blowers, key ones are the Australian Standard for Industrial and Commercial Gas-Fired Appliances. This standard determines how biogas systems downstream of blowers should be designed and installed, including flares, boilers and cogeneration units. Note, any imported flares must contain Australian approval for use. The system will need to comply with the safety requirements of the Australian Standard for Industrial Fuel-Fired Appliances. In regards to installation requirements, all mechanical installations must be certified by a licensed gas fitter and any electrical services must comply with the Australian Standard for electrical installations and be certified by a registered electrician. Care must also be taken siting the biogas flare relative to the CAL and must comply with the Australian standard for explosive atmospheres classification areas. As a general rule, a minimum distance of 6 metres is generally recommended. If the CAL is built with a significant height above natural ground level, consideration should be given as to whether the heat plume from the flare will affect the cover in wind conditions. Stainless steel pipeline construction is recommended for biogas piping downstream of the blower. All components of the biogas system, especially safety shut-off valves, blowers, meters and burner management system items, should be rated for operation with moist biogas, hydrogen sulphide, ammonia and other components likely to be present unless downstream of biogas conditioning equipment. Monitoring of biogas methane content and flow is recommended. Blowers and compressors should be located in open environments to minimise risk of biogas accumulation. Biogas with methane content less than 20% is non-flammable, so blowers should be designed to alarm at 30% and trip at 25% to prevent flare flameout. If blowers and compressors are in an enclosed room, electrical equipment should at minimum be suitable for operation in a Zone 2 gases area and the methane gas detection system designed to alarm at 20%. A suitable device to alarm at an appropriate level for hydrogen sulphide per local regulations should also be installed. Automatic shutdown of equipment should occur at 40%. The biogas flare should be installed to handle the entire design flow of biogas anticipated from the CALs, ensure that it is safely incinerated in the event of problems disrupting its use in boiler or cogeneration systems. This avoids holding excessive biogas volumes under the CAL cover and/or venting large volumes through overpressure devices. There are a number of components that must be supplied in the flare system. These include flame arresters at the flare inlet and between points of use and the blower, safety shut-off system, interlocking of monitoring system that measures methane content to trip the biogas flare if methane content falls too low, automatic ignition system, a blower management system which avoids drawing a negative pressure on the CAL cover which risks drawing in oxygen into the biogas. Some degree of biogas conditioning may be required when utilising the gas for higher grade users. Hydrogen sulphide and water can promote corrosion and lead to higher wear and tear in reciprocating gas engines. Water accumulation due to poor drainage can also impede the flow of biogas. Water and condensate can be easily removed using a knockout pot and drip tap, U-trap or condensate collection sump. Additional water removal can be achieved through refrigeration of the biogas, which cools the biogas to below the dew point temperature, forcing the water to condense. Removal technologies include water scrubbers, the use of ion absorption media, biological scrubbing and biological trickle filters. Ion adsorption media is the cheapest to purchase, but operating costs are expensive and not suitable for flows beyond 50 cubic metres per hour. For larger biogas flows, the best technology is a trade-off between high capital but low operating costs using biological filters or the reverse, low capital but high operating costs using water scrubbers. From an economic perspective, it is important to assess the cost of repair and replacement of corroded equipment with the cost benefit of conditioning the biogas through removal of hydrogen sulphide.